All right, hello everyone, and welcome to our first video of the 2026-2027 school year. This video is going over our material on the AP Chemistry Summer Prep document that you were handed at the end of your year in Pre-IB Chemistry if you are interested in moving forward with AP. Your objectives for this document was to memorize the polyatomic ions, memorize your 7 diatomic elements, your strong acids, your strong bases, and the names and symbols of the elements in the first 4 periods of the periodic table. You also need to be able to write and name formulas for ionic compounds, covalent molecules, and acids. You will need to be able to use stoichiometry to convert between substances. That can be grams to grams, grams to moles, moles to grams, particles to moles, so on and so forth. And then finally, you do need to know your sig fig rules. So first, let's look at our list of polyatomic ions. Of course, this is just a memorization slide, so there's not much I can tell you. However, I can give you a slight look into memorizing our sulfates, nitrates, chlorates, because there is a little trick to the naming of those. So let's look at chlorate because I have all of the polyatomic ions on there. Chlorate is our main, most commonly used ion for this polyatomic set. You can see that it has 3 oxygens. Now, if you just knew chlorate, you could remember that ite means there is 1 less oxygen. So we see it's the exact same polyatomic ion, except it has 1 less oxygen. And then hypo, ending in ite, is going to mean, again, we have 1 less oxygen. So again, everything's the same. We are just reducing by 1 oxygen. And then going in the other direction, if you had chlorate, and then you were looking at perchlorate, all that you're doing is adding 1 more oxygen. So instead of ClO3 minus, it's ClO4 minus. So that just kind of helps. For example, if you were given that you needed to write out nitrite, but you only memorized nitrate, well, I know, okay, nitrate is NO3 minus. Nitrite would be 1 less oxygen, so that would be NO2 minus. If you just want to memorize them outright, that's totally fine as well. Next up on our memorization list is the 7 diatomic elements. I always tell my students that these make a 7 on the periodic table. So if you start with nitrogen and end with iodine, it makes a 7 for 6 of the 7 diatomic elements, and then you just have to include hydrogen as well. So these are our 7 diatomic elements. What is a diatomic element, you may be asking? Well, that is just an element that when it exists by itself, it only exists as a pair. So for example, if I wanted to rewrite the chemical equation for creating water with hydrogen gas and oxygen gas, if I'm writing hydrogen by itself in this chemical equation, I will never have just 1 hydrogen there. It has to be 2 hydrogens together, which is why it is diatomic. Same with oxygen, so that would be diatomic. And if we're making water, we know that is H2O. So then obviously those are not balanced on either side. So you would then have to balance the oxygens and therefore balance the hydrogens, and then you have the chemical equation for forming water. So just keep an eye out for those 7 elements. If you ever have those by themselves in a chemical reaction, they have to exist with a 2 subscript. And if you wanted to know why that is, if we look at something like oxygen, we know oxygen has 6 valence electrons, and it is unstable as is. So if you just have a singular oxygen atom floating around in space, that is going to be an unstable atom. However, if we take 2 of those electrons from each atom and we share them between the 2, we now have a very stable molecule that can exist and not want to react with anything. And that works the same for all of our 7 diatomic elements. One more example, if you're looking at nitrogen, we know nitrogen has 5 valence electrons. That is unstable according to the octet rule. So if we have 2 nitrogens next to each other, in order to gain stability, they will bond to each other and share those electrons in order to gain stability, and both have a total of 8 valence electrons. All right, next up we have our 7 strong acids and our 8 strong bases. These will need to be memorized. These are very commonly assessed on the exam at the end of the year, and I will also bring them up in pretty much every unit. So I want to make sure that you know these, and I will give you some little tips that I give my students to remember them using the periodic table. So first up with our acids. We have 3 acids that come from the periodic table. What do I mean by that? That means we have a hydrogen paired with an element off the periodic table, and that is what my students like to call Clobri. So over here we have Cl, Br, and I. All that we're going to do is pair those with a hydrogen, and those will be our first 3 strong acids. So HCl, hydrochloric acid, HBr, hydrobromic acid, and HI, hydroiodic acid. Our other strong acids, I use a little jingle to help my students remember. It is clo, no, so, 3, 4, 3, 4. So clo, no, so, 3, 4, 3, 4. And then you go ahead and add your hydrogens. So the first 3 are only single hydrogens because all 3 of those polyatomic ions have a -1 charge. However, with sulfate, that has a -2 charge, so that needs 2 hydrogens. So those are our 7 strong acids. Now let's move on to our bases. Those are a little bit easier. The reason it's easier is because it makes a B on the periodic table, which I really appreciate. So a lowercase b on the periodic table, all we're going to do is take those metals and add on a hydroxide to the end of them. So for our group 1 metals, those obviously only make a +1 charge when they become an ion. So those only need 1 hydroxide paired with it to balance out those charges. Our 3 metal cations from group 2 are going to have a +2 charge, and since hydroxide is only a -1 charge, it's going to need 2 of those hydroxides to pair with it, which is why those look a little bit different. So those are the strong acids and strong bases that you have to memorize for this class. As you can see from our past couple of slides, the periodic table that is given to us for AP Chemistry does not have element names on it. So for the first 4 periods on the periodic table, I do need you to know the element name associated with the symbol. Now, because we're doing so much practice this year, these are going to come naturally to you. The 2 I want you to be really aware of is magnesium and manganese. Because the words look so similar, I find students mixing those up quite often, so just pay close attention to those 2 specifically. Before we go into naming ionic compounds, I do want to go over valence electrons and ionic charge in relationship to the elements on the periodic table. First, let's look at group 1 on the periodic table. We have all elements that have 1 valence electron. So every element in this column has 1 valence electron, meaning 1 electron in the outermost occupied shell. So let's say we're looking at sodium. Sodium has a total of 11 electrons. We know its first energy level is full with 2 electrons. Its second energy level is also full with 8 electrons. So now we have a total of 10. And then the final electron is in the 3rd energy level. And this is what's called our valence shell or our valence electron. So here, if we're looking at sodium and we want sodium to be more stable, we would look at whether sodium is going to donate or accept electrons. Now we know in order for it to be stable, it needs to have the octet rule or 8 electrons. Now, do you think it is more probable for sodium to gain 7 electrons to become stable or just lose the 1? The answer is just losing the 1. So with sodium, when it loses that valence electron, it now has 11 protons and 10 electrons, which, because it has one extra proton, it assumes a positive charge. So this procedure goes along with all of the elements in group 1. So all the elements in group 1, if they were to become an ion, they would have a positive 1 charge. Now in group 2, all of these elements have 2 valence electrons. So if we're looking at beryllium, for example, we have 2 electrons in its first energy level, and we have 2 in the second. Now, again, is it more likely to gain 6 electrons or to lose 2? The answer is to lose 2. So beryllium started with 4 protons and 4 electrons. By losing 2, it now has 2 extra protons. So it's going to assume a positive 2 charge, and that is the same process for all of the elements in group 2. So all the elements in group 2, if they were to become an ion, they would get a positive 2 charge. Now this process is the same with group 13. All elements in group 13 have 3 valence electrons. So again, it's more likely that they lose those 3 electrons instead of gaining 5. So by losing 3 electrons, which are negatively charged, they now have 3 extra protons, which are positively charged. And that is why group 13 elements would assume a positive 3 charge if they were to become an ion. Now looking in the other direction, we have group 15, which all elements in group 15 have 5 valence electrons. So let's say we are looking at nitrogen. So nitrogen has a full first shell, and in the second shell it has 5 valence electrons. So looking at probability, do we think nitrogen is more likely to gain 3 in order to get to a full octet or lose 5? The answer is gain 3. So nitrogen started off with 7 protons and 7 electrons, but now it just added 3 more electrons. We know electrons are negative, which is why nitrogen as an ion would have a negative 3 charge. Now group 16, 6 valence electrons. So if we're looking at oxygen, we have a full first energy level. And then in our second energy level, we have 6 valence electrons. So again, is it more likely to lose the 6 or gain 2? And the answer is gain 2. So if we are gaining 2 electrons, those are negatively charged, that means this ion would now have a charge of negative 2. And that is the same type of process with our halogens, or group 17. Because they have 7 valence electrons, they need only 1 more electron to become stable. So they would have a negative 1 charge if they were to become an ion. Now you might be wondering, well, what about the other columns that you didn't talk about? Those have more exceptions and reasons for why we're not including them. First of all, let's look at 14. Group 14 has 4 valence electrons. Typically in this group, we're going to have covalent bonding because, for example, carbon has 4 valence electrons. So instead of gaining 4 or losing 4, in order to gain stability, carbon's actually going to share out each electron to form a bond. And that is how carbon typically becomes stable. With our group 18, these are our noble gases. These already have 8 valence electrons. They're already stable, which means they're not very reactive and therefore do not want to bond ionically. And then finally, we have our transition metals here between groups 3 and 12. Those actually have multiple charges that they can assume, and we will talk about that later in the year. But for now, let's go ahead and move on to naming ionic compounds. So in your first class of chemistry, you should have talked about the different types of bonding that exist between atoms. There are different ways in which atoms can gain stability. Atoms can transfer electrons, and atoms can share electrons. Now, with ionic compounds, those electrons are being transferred, which means one of the atoms is going to give up or release electrons, and that other atom in the compound is going to accept those electrons. So in order for that to happen, you have to have a metal with a nonmetal, because as you can see on the periodic table, our metals are on the left side. They have low numbers of valence electrons, so they want to donate. And our nonmetals, which are on the right side of the periodic table, they have high numbers of valence electrons, so they want to accept. So if you are looking at a compound and you have to figure out, okay, how am I going to name this? If it is a metal and a nonmetal, your answer is ionic naming. So first step in naming an ionic compound is you are always going to write whatever the cation is first. So we're looking at the most basic one, sodium chloride, NaCl. The cation is always written first. All you are going to do is write it out. So sodium, we're just going to write out sodium. For the anion, if it is just a element, all you're going to do is write down the root word and change the ending to IDE. So this was chlorine. We're going to change that to chloride. And that is how you name an ionic compound. Now, of course, there are slight caveats to this rule. Number one is if you have a Roman numeral. We're looking at sodium, right? We know sodium is in group 1. It always has a positive 1 charge. We never have to think about that any other way. However, with those transition metals we talked about, those can have multiple charges. So in the name, we're going to have a parentheses of the charge of that metal. So that way you don't have to guess. So let's say we're working with FeCl3. We know iron is a transition metal, which means it can have multiple charges. So we're going to write out iron, and then we're going to put parentheses for the charge of iron. Now, how do we find that charge? Well, we know chlorine always has a -1 charge when it becomes an ion. If there are a total of 3 of them, that means the chlorine side is equal to -3. Since there's only one iron, that means that iron has to be +3 for the charge. So I'm going to put a 3 Roman numeral. Then again, same rule. It's chlorine for the anion. We're changing the ending to IDE. So iron 3 chloride. Another caveat to this rule is polyatomic ions. If ever you have a polyatomic ion for an ionic compound, you never change the ending of that for this. So let's say we have NH4OH. These are 2 polyatomic ions. We have NH4 plus, which is ammonium, so I'm just going to write that out. And we have OH minus, which is hydroxide. So for polyatomic ions, all you're doing is writing out their names. That is it. So a couple reminders from pre-IB is, number 1, please make sure when you were looking at these ionic compounds and creating formulas, the overall charge always needs to be 0. So if I'm looking at aluminum oxide and I give you aluminum oxide, the name, and you have to write the formula, I know aluminum is a +3 charge. And if it's aluminum oxide, that's oxygen, has a -2 charge. So I can see here, these do not have a common number. So I need to multiply each of them to get a common multiple. So here I have 3 and 2. So I'm going to multiply aluminum by 2, so I get +6. And I'm going to multiply oxygen by 3, so I get -6. So when I put those together, my overall charge is 0. So my final formula will be Al2O3. All right, now if you are looking at a substance and it is all nonmetals, typically you'd be going to these naming rules for covalent molecules. So if we're looking at something like C2H4. So C2H4, carbon and hydrogen, are both nonmetals. So that means we are going to our covalent naming model, which is here. The first rule is to write out the first element. So we have carbon. And it says to add a prefix if there is more than one, meaning if it's just one carbon, you just write carbon. But if there's more than one, then you need to write the prefix. So this would be dicarbon. Then you're going to write out your second element, hydrogen. However, you will always use the prefix for this one, and you will change the ending of the element to IDE, just like we did in ionic naming. So this would be tetrahydride. So C2H4 would be dicarbon tetrahydride. Very important mistake made a lot in pre-IB, not as much as an AP, but just as a reminder. We do not double up vowels. So when we do monoxide, like in carbon monoxide, it's not monooxide. You take out one of the O's. And the other one is there are never Roman numerals or charges in covalent molecules. So we're not using Roman numerals, we're not using charges. Typically, acids will present as all nonmetals with a hydrogen first in the formula. However, just know that there are exceptions to that. So as you can see in these three examples down here, all of them start with hydrogen, which is usually a clue to that it is an acid. So when we are naming acids, I want you to first ask yourself, does it have a polyatomic ion? If the answer is no, then you will always be using this framework here. You will write the word hydro, you will put the root word of the element, you will put the ending of ic, and then you will write the word acid. This is every single time you are getting that element from the periodic table. So if you had HBr, for example, that would be hydrobromic acid. If you had H2S, again, just an element from the periodic table, it would be hydrosulfuric acid. If you had H3P, that would be hydrophosphoric acid. If your acid does contain a polyatomic ion, it has a completely different framework, meaning you are not using the word hydro. All you're doing is taking that polyatomic ion name, changing the ending, and adding the word acid to the end. So what do I mean by that? Let's say I have phosphate, which is H3PO4. So the typical little mnemonic they use is 8 to ic and ite to us. So this is ending in 8, phosphate. So we are changing that to phosphoric acid. So that would be the name of H3PO4. Now, phosphorus and phosphate is a little different because we do add in that OR there. Same with sulfur. We don't call it sulfic acid. We call it sulfuric acid. Those are two exceptions. But let's do another one. Let's say I have H2CO3. This is carbonate. It has carbonate, which is CO3 2 minus. That is called carbonate. That ends with ATE, so we are changing it to IC. So the name of this acid would be carbonic acid. And then if it ends in ITE, you're just changing the ending to OUS. So let's say we had H2SO3. This is SO3 2 minus, which is sulfite. So because it's ending in ITE, we're changing it to OUS. So it'd be sulfurous acid. But if it was H2SO4, which is SO4 2 minus, that's sulfate. So that would be sulfuric acid. And again, sulfur is one of those little exceptions where we do more than just the root, we do the whole word. So keep that in mind. All right, so now that we went through all of the naming rules, let's go ahead and do your summer prep problems. So the first one is HClO. First thing I want you to notice is the H in the beginning. That should make you think acid. ClO minus is our polyatomic ion here. So since we have a polyatomic ion, we are never using hydro. Remember, that's only if you just have an element. So here we have a polyatomic ion. So we need to look at the ending. ClO minus is hypochlorite. It ends in ITE. ITE changes to OUS. So the name of this would be hypochlorous acid. Next we have SO3. There's no H in front. We have sulfur and oxygen, both of which are nonmetals. So that is going to tell us that we are using covalent naming rules. So we're going to write out our first element, sulfur. Remember, for the first one, we do not write mono. We do for the second one, but not for the first one. So sulfur, and then we have 3 oxygen, so it's going to be trioxide. Remember, change the ending to IDE. Then we have NaBr, no H in front, so not an acid. We have sodium, which is a metal, and we have bromine, which is a nonmetal. So that should make you think ionic compound. So remember, for ionic naming, you're just going to write the name of the cation, which is sodium. It is not a transition metal, so we do not do Roman numerals. And then we have bromine that we're going to change to bromide. Next up, we have NiP2. Nickel is a metal. Phosphorus is a nonmetal. So again, we have ionic. Now, we know nickel is a transition metal, so we need to identify the charge and put it in for Roman numerals. So if phosphorus, that's in group 15, so it's going to have a -3 charge. If we have 2 of them, that means totally we have a -6 charge for our anion, which means for our cation also has to be a +6 charge. Since we only have 1 of them, we know nickel has to be a +6 charge. So the name would be nickel 6 phosphide. Next up, we have a polyatomic cation and a polyatomic anion. Electrostatic attraction, positive and negative, that's going to be an ionic compound. Now, because they are both polyatomic ions, we know we are just writing out the polyatomic ions. We're not changing anything for ionic compounds. So that's going to be ammonium phosphate. Next up, we have an H in front, which, what does that tell us? Acid. Now, is this a polyatomic ion? No, it is not. It's an element from the periodic table, which means we are starting with hydro. This is fluorine, so it's going to be hydrofluoric acid. Next up, we have lithium and we have sulfur. Lithium is a metal, sulfur is a nonmetal. So again, this is ionic. Lithium is not a transition metal, so we are just writing lithium and then changing the ending to ide, sulfide. Then we have SF6. Sulfur is a nonmetal, fluorine is a nonmetal. Because they're all nonmetals, it's going to be a covalent molecule. We only have one sulfur. Remember, you do not write mono for the first one. And then we have 6 fluorines. So 6 is going to have hexa as a prefix. So it's going to be hexafluoride. Then we have Cu2S. Copper is a metal. It's actually a transition metal. And sulfur is a nonmetal. So transition metal, remember, we need to do a Roman numeral. So we need to figure out the charge. So sulfur is in group 16, which means it needs 2 electrons. It's going to have a -2 charge, which means our overall charge for the cation side is +2. However, there are 2 coppers. So each copper has a +1 charge. So when we write out the name of this, our Roman numeral will be a 1. So this would be copper 1 sulfide. So we here have KMnO4. K, or potassium, is a metal. MnO4 is a polyatomic anion. So it has a charge of -1. Which is not important because it's not a transition metal. So we have potassium, and MnO4 minus is called permanganate. And one thing before we move on that I really want you to get in the habit of is looking at all of these formulas and being able to tell me what kind of bonding is happening. So go ahead and pause the video and write down or circle all of the formulas that are ionic. So you should have circled sodium bromide, nickel 6 phosphide, ammonium phosphate, lithium sulfide, copper 1 sulfide, and potassium permanganate. And that is going to come in handy when we start doing these harder units to already have that ready to go. So you will notice that going from formula to name is a lot easier than going from name to formula, because when we go from name to formula, you do have to identify all the charges to get the subscripts correctly for ionic bonding. So first, let's start with calcium sulfide. Calcium is a metal and sulfur is a nonmetal, so that's going to be ionic bonding. So with ionic, we do need to get the charges and make sure they balance out to 0. So looking at your periodic table, calcium is in group 2, which means it has 2 valence electrons. So when it becomes an ion, it loses those 2 electrons and forms a +2 charge. Sulfur is in group 16, has 6 valence electrons, wants to gain 2 to get to 8, which means it's going to have a -2. Now you can see these already balance out to 0. So I just need one of each. So it'd be CaS. Next up, we have silver iodate. So silver is a metal, iodate is a polyatomic ion, negatively charged. So silver is Ag, and we will go over this a little bit later in the year, but Ag or silver only has 1 charge. So we don't actually write Roman numerals, even though it's considered a transition metal. So Ag only has a charge of +1, and iodate is IO3 with a -1 charge. So you can see +1, -1 already cancel out, so we are just writing one of each. And that is our answer for that one. Keep in mind, we do put parentheses around polyatomic ions only if there are more than one. So here we only have one iodate, so we're not going to write parentheses. Moving on to carbon monoxide. Carbon is a nonmetal. Oxygen is a nonmetal. We can tell this is covalent bonding because it has prefixes. So remember, we don't write the prefix for the first one, but we are assuming it. So we have one carbon and one oxygen. Tin 4 cyanide. That Roman numeral is telling me the charge of my metal. So that means tin has a positive 4 charge. Cyanide is Cn minus 1. So if we have positive 4 and negative 1, we're going to need 4 of these to balance out that tin. So it's going to be tin, which is Sn, and then we're going to have Cn with a subscript of 4 because we need 4 of those to balance that out. Next we have nitric acid, obviously an acid. So if I have ic, that means it used to be 8. So nitrate. This is when knowing your polyatomic ions is very important. So nitrate is NO3. It has a minus 1 charge, which means I only need 1 hydrogen. So HNO3. Then we have potassium carbonate. That's a metal and a polyatomic ion that's negatively charged. So potassium is a positive 1. Carbonate, CO3, 2 minus. So I'm going to need 2 of those potassiums to balance out the carbonate. So it's going to be K2CO3. Then we have hydrosulfuric acid. It's an acid that starts with hydro, which means it's directly from the periodic table. So we have sulfur, which we know has 6 valence electrons. So it's going to need 2 hydrogens to complete that octet. So it's going to be H2S. Then we have some prefixes here that should give you an idea that it is covalently bonded. So we have 2 borons and 4 bromines. So B2, Br4. And then we have zinc borate. So borate is not one you have to memorize. I have never seen it on the AP exam, but you never know. So zinc is another one of those metals that only have 1 charge. It's one that you do have to memorize. So zinc has a positive 2 charge always if it becomes an ion. You don't have to memorize it right now, but you will in the future. And then borate is BO3, 3 minus. So as you can see, we have a different number here, 2 and a 3. So we're going to do the common multiple of 6. So we're going to need 3 zincs and 2 borates. And then finally we have copper 2 phosphate, which means copper has a positive 2 charge. And we know phosphate is PO4, 3 minus. So again, we're going to need 3 of the coppers to get to positive 6. And 2 of the phosphates to get to negative 6. All right, so this is not technically on your list, but I did want to go over it just in case you were not familiar with scientific notation. So scientific notation is just a way for us to easily write really big or really small numbers. So just to remind you, a really big number is going to have a positive exponent. So if I have a number of like 36 million, that's a big number. It's greater than 1. So that's going to have a positive exponent. So you're just going to move the exponent 7 times to get to a number between 1 and 10. So it's going to be 3.6. Since we moved it 7 times, it would be times 10 to the 7th. So that is scientific notation. Big number, positive, small number, negative. And by small number, I just mean less than 1. All right, significant figures. Everyone always hates sig figs every single year. Now, pretty much everything is significant except for 2 scenarios. Number 1 is leading zeros, which is technically number 3 here. So leading zeros literally never count. There is not any situation in which leading zeros, the zeros that come before any numbers, count. They are never significant, never count them. Now, trailing zeros is a different story, because if there is a decimal in the number, then trailing zeros do count. That's what it says in number 4. However, if it is a whole number, then trailing zeros do not count. So here, when we have 1200 or 5300, those zeros do not count because there's no decimal point. So if you just remember Rule 3 and Rule 5, which are the ways in which numbers do not count as significant, then you can just remember that everything else counts as significant. But if you'd like to pause and read through all of this, I invite you to do so. All right, and now for everyone's favorite part. Actually, it is one of my favorites because it's very therapeutic. But now we're going to dive into some stoichiometry, which is just a fancy way of saying we're converting between one thing and another thing using a balanced chemical equation. So first, how many grams are in 2-mole sample of iron? So this doesn't even have a chemical equation. It's just nice and simple. It's one conversion factor. So how many grams, which means I am solving 4 grams. Then I am given 2.8 moles of iron. So that is what I'm starting with. 2.8 moles of iron. Now, here comes my conversion factor. I want to get rid of moles of iron. So on the bottom, I'm going to do 1 mole of iron. Now, I want to get to grams. I know from the periodic table that 1 mole of anything is equal to its molar mass. So if I have 1 mole of iron and I find iron on my periodic table, I can see that its molar mass is 55.85 grams of iron. So now looking at my math here, moles of iron is gone. I'm left with grams of iron, which is what I am solving for. So now I just do my math. 2.8 times 55.85. That gives us 156.38 in the calculator. Now, the sig fig rule when multiplying or dividing is you're going to go with the smallest number of sig figs in your given data. So here we were given 2.8, which is 2 significant figures. So our answer is going to be in 2 significant figures. And how do we make this 2 sig figs? Well, I know the cutoff is here. This is going to round up to 6. And I still have to put a placeholder here because if I just do 16, that's way different than 156. So the answer is going to be 160 grams of iron. All right, so for this one, we are given our balanced chemical equation. It says how many grams of KCl are produced from 1 gram of chlorine gas and excess potassium. So this is already telling me that potassium is my excess reactant, which means I already know that chlorine gas is my limiting reactant. So whatever amount of chlorine gas I have, I'm going to use that amount to convert to my product because that will tell me how much I can actually make. So if I have what I'm starting with, which is 1 gram of Cl2, I want to get 2 grams of KCl. So as you can see, we are in different substances right now. So if you want to convert between one substance to the other, you have to be in moles. So our first step is to get rid of grams and to get into moles of chlorine gas. So I know in 1 mole of chlorine gas, that's going to be equal to the molar mass on the periodic table. Now just remember, we're not putting 35.45 in here. We are multiplying that by 2 because we have 2 of them. So 35.45 times 2 is going to give us 70.9 grams of chlorine gas. Now that I am in moles of chlorine gas, I know I want to get rid of that, and I want to get 2 moles of KCl. Now this is the only time, this is called the mole ratio. This is the only time in which the number in front of mole is not 1. and that's because you're getting the numbers from the or from the balanced chemical equation. So KCl, I have 2 moles of that. Chlorine, I have 1 mole of that. Now, if it was asking for moles of KCl, I would be done, but it's not. It's asking for grams of KCl. So I know in 1 mole of KCl, it's the molar mass of KCl. So I'm going to add those values together. K is 39.1 and Cl is 35.45. So that gives me 74.55 grams of KCl. And now, in my calculator, I will multiply and divide across so that I can get my final answer. So I'm going to go backwards because I already have 74.55 in my calculator. So 74.55 times 2 divided by 70.9 is going to give us 2.10296. And I need to look at sig figs. So I am given 1.00, which is 3 significant figures. So my answer needs to also be in 3 significant figures. 2 does not round up, so my final answer is 2.10 grams of KCl. What is the percent composition by mass of each element in calcium phosphate? So whenever you're doing percent by mass, it's just the mass of whatever element you are looking for divided by the total mass of the compound and then multiplied by 100. So we are doing calcium phosphate. So our first step is to get the total mass. So we're going to get the total molar mass. First up, I have 3 calciums. Calcium is 40.08. Then I have 2 phosphorus. So I have 2 times 30.97. And you'll see why I'm doing this separately in a second. And then oxygen, I have 8 total because I have 2 times 4. So 8 total times 16. So 40.08 times 3 is going to give us 120.24. Remember, we never round until the very end. Then we have 2 times 30.97. That gives us 61.94. And then we have 16 times 8, which is 128. So now we're going to get the total of that. That's going to be 310.18. So this is our total mass. This is what we are dividing each number by. So first let's start with our percentage of calcium. So I want my grams of calcium, which is 120.24, divided by my total mass of 310.18 times 100. That's going to be 38.8% calcium. And in a question like this, if it's not telling you what sig figs to use, the default sig fig is 3. All right, now let's do percentage of phosphorus. So that's going to be 61.94 divided by 310.18 times 100. So that's going to give us 19.97% of phosphorus, which is going to round up to 20.0% of phosphorus. Now, from here, to make sure it always adds up to 100, I always like to subtract it from 100 at this point just to make sure it all adds up. So we're going to take 100% minus 20 minus 38.8, and that gives us 41.2% oxygen. And those would be our final answer. All right, so here we have a limiting and excess reactant problem, and it does not tell us which is which, so we have to solve for it. How many grams of AgCl result from the reaction of 1.3 grams of sodium chloride and 3.5 grams of AgNO3? So we need to find out how many grams of AgCl is actually formed from this reaction. So both of these numbers are being solved into grams of AgCl. So let's start with 1.3 grams of NaCl and 3.5 grams of AgNO3. First step when we are doing stoichiometry and we want to get to a new substance is we have to get to moles. So in 1 mole of NaCl, I'm going to have the molar mass of NaCl. And in 1 mole of AgNO3, I have the molar mass of AgNO3. Now that I am in moles, I can go ahead and convert to AgCl. Now this is all 1-to-1 ratio, so it's kind of redundant, but to show the stoichiometry canceling out, I am going to redo it. So moles of NaCl, 2 moles of AgCl, and moles of AgNO3, 2 moles of AgCl. Again, all 1-to-1 ratio, so it's going to be all ones. And then finally, we want to get to grams of AgCl. Now, could you solve for this and then only do this for the limiting reactant? Yes, but I don't like to do that. I like to do all my math at once. So now I want to get to grams of AgCl, and I know in 1 mole of AgCl, I'm going to have my molar mass of AgCl. So I just need to find my molar mass of AgCl. So now I can go ahead and solve each problem. So I have 1.3 divided by 58.44, press equals, and then multiply by 143.32. Rounded to 2 sig figs, that would give me 3.2 grams of AgCl. And now for my bottom equation, I have 3.5 divided by 169.88, and then multiplied by 143.32. So that's going to give me 3.0 and 2 sig figs. Now remember, if we're looking at a chemical equation, right? I'm putting NaCl into the same container with AgNO3. It is highly unlikely that I have the perfect amount of each substance to make the exact amount of product and have 0 reactants left over. That's very unlikely. Most likely you're going to have one of those 2 reactants left over. So the limiting, the one that is gauging the whole reaction, is going to run out before you can use all of the other reactant. So in this case, we are looking for the smaller number, and that is the 3 grams. So how much AgCl can actually result from this reaction? Only 3 grams. Because after 3 grams, we're going to run out of our limiting reactant, and we're going to have leftover NaCl. So limiting reactant is going to be AgNO3. Excess reactant will be NaCl. And this number, 3.0 grams of AgCl, that is what we call the theoretical yield. You will hear of that term, so I just want to make sure you know it. Now it says how much of the excess reactant is left over. Now I know that I can actually make this much AgCl. So what we're going to do is we're going to take that 3 grams, and by putting 3 grams, we're actually putting in some error. So let's use the real number from our calculator so that we don't have any error in our question. So from the calculator is 2.953. Let's use that. Grams of AgCl. And that's just best practice. If you were to put 3 grams of AgCl in the next question in an AP chemistry problem, they would still give you the answer, just so you know. All right, so I have this much AgCl actually made. So if I take this and I convert it back into my excess reactant, that's going to tell me how much of it was used. So let's start there. I need to get out of grams of AgCl and into moles of AgCl. So that is 143.32 grams. Then I need to go from moles of AgCl to moles of excess reactant, which is NaCl. Everything's a 1-to-1 ratio. And then I need to go back to grams of NaCl. So now let's do that math. So divided by 143.32, then multiplied by 58.44. That's going to give me 1.204, because we're not done, grams of NaCl used. What is the question asking? How much is left over? So if I started with 1.3 grams and I used 1.204 grams, that means I have 0.096 grams of NaCl left over at the very end. So that would be my final answer. All right, and finally, if the reaction yielded 2.7 grams of AgCl, what is the percent yield and the percent error for the reaction? So I always tell my students percent yield is where it is at. So percent yield is actual over theoretical times 100. So the actual yield was 2.7. The theoretical yield was 3. So 2.7 divided by 3 times 100 is 90% yield. Now, percent error is a little bit different. Percent error is actual minus theoretical absolute value over theoretical times 100. So that's going to be 2.7 minus 3, and absolute value would be 0.3, divided by theoretical, which is 3, times 100. That's going to give us 10% error. Now, if you didn't notice already, they're going to add up to 100. So if you already knew that and you knew the percent yield was 90, you could just tell me that the percent error was 10, but that is how you solve for it. All right, these are a beast of problems, but I hope you followed. If not, I would probably watch it again or come into office hours, and I'm happy to explain it a little bit differently. All right, what is the empirical formula of zircon if its percent composition by mass is 34.91% oxygen, 15.32% silicon, and 49.76% zirconium? So for empirical formula, I like the little jingle that says percent to mass, mass to mole, divide by small, multiply until whole. So percent to mass, mass to mole, divide by small, multiply till whole. Those are the 4 steps to get you to your empirical formula. Now, of course, it's not always perfect, but that's the main framework, if you will. So the first step, percent to mass, all you're doing is changing the percent sign to a gram sign because we're assuming it's out of 100 grams. So we have 34.91 grams of oxygen. We have 15.32 grams of silicon, and we have 49.76 grams of zirconium. That's the first step. It is done. Second step, grams to moles. We know to get to moles, we need to divide by molar mass. So I know in 1 mole of O, I have 16 grams of O. In 1 mole of silicon, I have 28.09 grams of silicon. And I know in 1 mole of zirconium, I have 91.22 grams of zirconium. So that is getting them into moles. Really common for students to look at this first one and be like, oh, oxygen is diatomic, I need to put it out of 2. No, you only do that when you're writing a chemical equation and it says that oxygen is reacting with something else, then you're writing O2, but not in this scenario. We're just talking about O individually. So for the first one, we have 34.91 divided by 16. That's going to give us 2.1819 moles of oxygen. Then for silicon, we have 15.32 divided by 28.09. That's going to give us 0.5454. And then for zirconium, we have 49.76 divided by 91.22. That's going to give us 0.5455 moles of zirconium. So now the next step is to divide by small. Obviously the smallest is silicon and kind of zirconium. It's really close. So we're going to divide all of these by 0.5454. Obviously it's going to be 1 for these. And then it's going to be 4 for this one. So we are already in whole numbers, which is nice because we do not have to multiply. So all we're going to do is assign these numbers to our symbols, and that is our formula. So O4 SiZr is our empirical formula. All right, in the very last question of our summer prep document, how many atoms of aluminum are in 63 gram sample of Al2O3? So we have 63 grams of Al2O3. It's asking for atoms, which is Avogadro's number. Avogadro's number is 6.022 times 10 to the 23rd particles, which particles is like an umbrella term for molecules, formula units, atoms, really whatever you have. So to simplify Avogadro's number, it's like saying you have a dozen roses or a ream of paper, which is 500 pieces of paper. It's just a number that's a constant for us so that we know how many of these aluminum atoms are in this amount of aluminum oxide. It's just a constant that we can use that has been proven through scientific research. So looking at what we are given, which is 63 grams, I cannot use Avogadro's number because I know it is equal to 1 mole. So I need to first get this number into moles. So I know in 1 mole of Al2O3, it is the molar mass of Al2O3. And that is 101.96 grams. So now that I'm in moles, I can go to atoms. I know in 1 mole of Al2O3, I have Avogadro's number, or 6.022 times 10 to the 23rd particles. Now, that just brought me to particles of Al2O3. I'm specifically asking for aluminum. So I know in 1 mole of Al2O3, I have 2 moles of aluminum. So that is going to get me to aluminum. So now I can go ahead and solve. 63 divided by 101.96 times 6.022 times 2. So that gives me 7.4 times 10 to the 23rd atoms of aluminum. All right, I hope this video helped. I'm sorry it was so long, but I hope that you now understand everything in our summer prep document. See you soon. Have a great school year.